presentation, we'll walk you through Chapter 3, Descriptive Statistics. I'll go through a general lecture like we would in class, and I will stop periodically to show you different examples in Excel. There will be a separate video where I show you how to work out the same problems by hand. So what is descriptive statistics? Basically, it's a discussion of a measure of location within our data set. So those are things that we can point to and allow us to describe our data. Most commonly what you think of is the average, which is the mean. So we're going to discuss that. But before we get into that, we need to know whether we are discussing just a sample or an entire population. For the population, that assumes that you know every single possible data value. A population would be, you want to look at the entire world's population, you need to know the sex of every single individual on the planet. That's really, really hard to get. So what we would most likely do is select a sample of that population. So survey the sex of individual members of the populations from each of the different countries, and then we would use those sample statistics to extrapolate information about our population. So technically we calculate sample statistics, which are estimates of population parameters. Our sample statistics are then a point estimate corresponding to that particular population parameter. So the first one you normally think of is mean. Another word for that is average. Median is like the middle number. Mode, the number that comes up the most often. And then percentiles and quartiles, think about where you wanted to know how much you make relative to someone else, or how you scored on the ACT relative to those who took it. So these are, just a way of locating where you are in the data stream. Mean, the average of all data values. So for a sample value, x bar, the mean is the sum of all of the individual observations divided by the total number of observations in your sample. The same goes for the population. So the sigma in the numerator means add everything up, and then we're dividing by n the number of observations. Excel uses the formula average. So here's an example. Efficiency apartments are randomly sampled in a small college town. The monthly rent prices for these apartments are listed below. So we have a series of 70 monthly rent prices listed. We want to know what is the mean or average rent price. So we take all of the prices, all 70 of them, add them up, and divide by 70. So the average monthly rent on an efficiency apartment in this town is $490.80. The median is the value in the middle when the data is arranged in ascending order. It is a measure of location most often reported for annual income or property values. Okay, so if you have an odd number of observations, calculating the median is really easy. You order the observations from smallest to largest and choose the middle number. If you have an even number of observations, it's a little more tricky because you'll have to take the average of the two middle numbers. So in our example here, we arrange all of our data from lowest at 425 over here to highest at 615 here. And then since we have 70, that's an even number, we have to take the average of our two middle observations. Well, in this case, they're both $475, so the median rent here is $475. So let's go and look at our work that we would be doing if we were doing this in class. So I have a note here that we would do number 1 together in class, and you would do number 3 on your own. So if you'll look here on our data sets, I have 1, 13, and 3, 15. These are basically, what's happening is the textbook is reusing the data from problems. So I'm going to work out the answers for question number 1 right now, and you're going to move on and do question number 3 when you work on this on your own. So the first thing it asks us to do is calculate the mean. So we use the average function to calculate the mean, equals average, open parenthesis, and then select our data. Close parenthesis, enter. So our average observation here is 15. This is question number 1 on page 107. It just says consider the following data values, compute the mean and median. So there's no other interpretation here other than the mean is 15. For the median value, we'll hit equals median. And here we don't actually have to worry about arranging it. It would do the arranging for us. It would also do the calculation for us if we had an even number of observations. And again, I said I would present a separate video where we work out these calculations through hand. Okay, so back here. Mode. Mode is the value that occurs with the greatest frequency. So basically, it's the number that shows up the most. If you only have one number that shows up the most, it's single mode. If you have two numbers that show up equally frequently, it's called bimodal. If you have more than two numbers that show up equally frequently, it's called multimodal. Excel works best when you're just calculating, or when your data just has a single mode. And our example here would be the mode here is 450. That means that of all of the 70 apartments surveyed, 450 was the most common monthly rental amount. It doesn't mean it was the average, it just means it was the most common. Percentiles. They provide information about how your data is spread over the interval from the smallest value to the largest value. So you can arrange your data, smallest to largest. Let the percentile of interest I equals the quantity P divided by 100 times N. Okay, what does that mean? Basically, the percentage of interest is going to be your percentile times your number of observations. So for a percentile P of 80%, it would be 80 divided by 100, or 0.8 times N. For 90%, it would be 0.9 times N. So it sounds like, it looks like a complicated formula. It's just basically saying, take your percentage, put it in decimal notation, and multiply that by the number of observations that you have. For Excel, it's percentile data, comma, percent, and that percent also needs to be in decimal notation. So here we can look at a percentile example. The 80th percentile of apartment rents is what? So 80 divided by 100, that's 0.8 times 70, that gives me 56. So 56 itself means nothing. That means that we're looking at the 56th observation. Okay? So the 56th observation is 535. The way I interpret that is at least 80% of my apartments are less than 535. Okay? At least 80% of my apartments are less than 535. So the 80th percentile is 535. Let's look, quartiles work in pretty much the same way, except that quartiles are specific percentiles. So the 25th percentile is the first quartile. The 50th percentile is the second quartile, and the third percentile is the 75th. I'm sorry, the third quartile is the 75th percentile. So for the Excel formula, you use quartile, open parenthesis, highlight your data, comma, the number of the quartile you're interested in. So 1 for 25%, 2 for 50%, and 3 for 75%. So let's look at another. So here we have a list of 20 cities and their hotel rates per night, their average hotel rates per night. So we were asked to calculate a mean, a median, a first quartile, and a second quartile. So again, we can calculate the mean using the average function. So the average hotel rate per night is $159.05. The median rate or middle dollar amount of the rental per night is $161. The first quartile, first quartile, highlight my data, and the first quartile or 25th percentile, I select 1. So my 25th percentile is $137.75. In other words, 25% of the hotel rates per night are less than $137.75. My second quartile, I'm sorry, it asked for my third quartile, not my second quartile. So let me change that. So my third quartile, the 75th percentile, is $168.50. So 75% of the hotel rooms cost less than $168.50 per night. Measures of variability. We have the first one, the easiest one, range. So smallest to largest, largest to smallest, and the difference between them. Variance, which is a measure of the distance from the mean, and standard deviation, which is the square root of the variance. So range is the difference between the largest and smallest values. The interquartile range is the difference between the third quartile of your data and the first quartile of your data. Quite conveniently, we just learned to calculate quartiles, so that should make that relatively easy. So if we look here at our first example, this is referring to our efficiency apartments. We arranged the data from smallest to largest. The cheapest rent was $425. The most expensive rent was $615. So the range there is $190. Basically, that means there's a $190 differential in what you could be paying per month for your apartment. So that kind of tells you, the spread of potential rents that you're looking for and how much that would potentially differ. So we are going to practice now this idea. We're going to work on question number 13, which uses the same data as question number 1. The question itself can be found on page 118, and it asks you to calculate the range and the interquartile range. Okay, so to get the 25th percentile, we have a couple different ways of doing that. We're going to need it to get the interquartile range. So I can say equals percentile, percentile, open that up, highlight my data, comma 0.25, and that tells me that my 25th percentile is 12. Alternatively, I can do that same calculation using the quartile notation, because the 25th percentile is the first quartile. Okay, and I can follow along the same thing for my 75th percentile, or third quartile. Ends parenthesis there. Okay, so 25% of my observations are less than 12, 75% are less than 16. My overall range is the distance between my highest and lowest. So my overall range here is my lowest observation, the minimum value here, minus my maximum value in that same data range, or max minus min, min minus max. I'm going to go back and delete this. Okay, so my range, the actual range, not the interquartile range, but the actual range is the maximum observation in my data sets minus the minimum observation in my data sets. So that's one way of doing it, and I have a range of 10. Another alternative, instead of using maximum and minimum, I can actually go here into my data, highlight my data, click Data Sort. I can sort column A, because I have no other definition for it, it's just in column A, based on values smallest to largest, and it's not going to do anything when I click that because it's already, linked smallest to largest. And I could just go in and subtract my smallest number from my largest number. That would also get me that 10. Now, something else I need to calculate, and I didn't make a cell for, is the interquartile range. So the interquartile range is the third quartile minus the first quartile. So third quartile minus the first quartile, that gives me my interquartile range of 5. Okay, so now I would ask you to work on question 15, which basically just requests that you do these same calculations with this second data set, the same data set that you worked on for problem number 3. Okay. Variance. Variance is a measure of variability that uses all of your data. It's based on the difference between each observation and its mean. Now, normally at this point, students kind of freak out when they see the formulas. Remember, in this video, we're just dealing with the Excel calculations, and there will be a separate video showing you how to do this by hand. However, we are going to go over the formula because I'm sorry to have to point out, you will need to be able to do this calculation by hand. So let's break down the formula. We're going to focus only on the sample section, since in very rare cases do we actually deal with an entire population worth of data. So sample variance. Okay, let's look at our numerator. We have the sigma, that's the summation sign. That means we're going to add up a whole bunch of stuff. Or what are we going to add up? We are going to add up, we see x sub I. That's each individual observation minus x bar, which is its mean, squared. And then we are going to add up all of those observations, all of those deviations from the mean, and we are going to divide that by n minus 1, the total number of observations in your sample minus 1. Okay? Or we will be using the variance function in Excel. So now, standard deviation is the square root of the variance, is a measure in the same units as the data, and it's more easily interpreted than variance. So when you're doing a variance, you're looking at the deviation between your actual observation, xi, and its mean, x bar. Now, those deviations can be above and below the line, meaning your individual observations can be greater or less than the mean. Well, if we didn't have that squared thing in there, then deviations above the mean and below the mean would cancel each other out. So what we do is we square the numerator of that equation to make sure that we don't have any canceling. Unfortunately, that makes the units really, really hard to interpret because the units of our variance are then percentage squared. So that's really hard to understand. So normally people calculate a variance, but when they start quoting things, they actually quote the standard deviation because that will just be interpreted as a percent. So it takes away that impact of the squaring. So to get a standard deviation, you can calculate the variance and then take the square root of it, or you can just calculate the standard deviation outright with the STDEV function. Now on your calculators, you can use the square root key, or you can also raise something to the 1/2 or 0.5. If you raise your number to the 0.5, that is the same as taking the square root of it. Okay, so let's see an example of this. Go back to question number 13, variance and standard deviation. So equals variance, highlight my data. So my variance is 16, but that's percent squared. I don't even know what this means. Equals, okay, so equals STDEV to do my standard deviation. And I come up with a standard deviation of 4. At this point, I would ask you to calculate the variance and standard deviation of number 15. Okay, so now I come, after I've made you go through all of those fun and exciting calculations where you do them individually in Excel, I now show you how to do it all in one step. And at this point, this is why I'm glad this was on video, because at this point in class, people are ready to throw things at me and go, why'd you make me memorize all those formulas? Okay, so there is a really simple way in Excel to have Excel calculate for you the mean, the median, the mode, the mean, median, mode, variance, and standard deviation. And what you're going to do there is you're going to go into data, data analysis, select descriptive statistics, and then when you're in descriptive statistics, make sure to select summary analysis. So let's go and look at an example. We'll go back to our example hotels here, number 5, and we calculated the mean, the median, the first quartile, and third quartile. So I can just click on any open cell here, go to data, over here to data analysis, click on that, select descriptive statistics, click OK, enter my data. Now, I started with my rate per night, so I'm going to select in there that I have a label in my first row. I want my output. Now, be really careful here because I select my output and I have to click again in this cell. Otherwise, it's going to go and change my input range, which can be very frustrating. So I select my output range, click in this box before I go and click my any open cell, and then I want to select summary statistics. I'll click OK. And this tells me the average rate per night, the median rate per night, the mode, the standard deviation, the variance, the range, the min, the max, count, all kinds of fun and exciting stuff. And however, I would still need to go and calculate my first and third quartiles. So unfortunately, it does not give you your quartiles. At this point, I would ask you guys to practice doing the same thing with tax costs, which is question number 8. If we look back, question number 8 in that same data that we've hopefully worked through before, or we will work through together again in class. Now, if you'll notice, one of the things that we discussed in the descriptive statistics, one of the things that you saw on there is skewness. We talked a little about skewness in the past, and I said it was the degree of shiftiness, and then we said, skewness when you're looking at it is the exact opposite of what you expect it to be, all that kind of stuff. So I've given you a formula for skewness. I will not make you calculate this formula, I promise. I will, however, ask you to look at data and tell me if it is skewed in one way or the other. But this is one formula that I will never make you calculate. So in our first picture there, we have a skewness of 0. That is a completely symmetric data set. The mean and the median are equal. Our next data set is skewed to the left. That's known as a negative skewness, where the mean is less than the median. And our final data set down at the bottom is skewed to the right, which is known as positive skewness, where the mean is greater than the median. So negative skewness mean less than median, positive skewness, mean greater than the median. So if data is skewed, it just means that there's more observations either above or below the mean than you would normally expect. So here, our example, our data here for our apartment sample was skewed. It's 0.92. It's skewed to the right. Well, what exactly does this skewness mean? What should we expect from, how is it different from a normal distribution? What's going on here? So our z-score denotes the number of standard deviations of the data value that it is from the mean. So if we're following a standard normal distribution, we will see that 68.25% of our data is within one standard deviation of the mean. 95.44% is within two standard deviations of the mean, and 99.72% is in three standard deviations of the mean. Now you're getting this from the picture, but what we're looking at there, that's actually the population parameters, not the sample parameters. You would notice by the different use of Greek symbols there. But mu means mean, sigma is standard deviation. So mu is the mean, and then those first dotted lines at the 68%, mu minus one standard deviation and mu plus one standard deviation. So that's what they're talking about there for that calculation. Now moving over to our actual formula, this is for our sample. Your z-score is your observation minus the mean divided by the standard deviation of that variable. So data values less than the mean have a negative z-score. Data values greater than the mean have a positive z-score. Okay. Let's go and calculate the z-scores for question number 13. Remember our formula, xi minus x bar, that quantity, divided by s. So for number 13, we can go in and we want our z-scores. And the easiest way to do that using Excel is to say standardize. Standardize. Okay. Nope, go back up. Select that one. Why are you not clicking? Okay. So standardize. I need x, the mean, and the standard deviation. Okay, I know this. Here's my individual x. That's my observation. Here's its mean. And here is its standard deviation. So I just select the information. And I get a negative z-score, meaning that the data value is, meaning that the data value is less than the mean. So 10 is less than my mean of 15. Now, I want to be able to just drag these things down. So I'm going to F4 my mean because that's going to be constant, and I'm going to F4 my standard deviation because that's going to be constant. And then I can just, drag down these, drag down these values. And it's going to do that calculation for me. Now, what is the purpose of calculating this z-score? I calculated this z-score in order to determine if there are any outliers. An outlier is an unusually small or unusually large observation in my data set. A data value with a z-score of less than -3 or greater than +3 would be an outlier. So are there any outliers in here? The answer is no. Okay? You can practice doing the same thing with problem number 15. Come on. So here is our example for our apartment rents. They use the standardized function to calculate the z-scores of each of the average monthly rents. And since none of these observations are less than -3 or greater than +3, there are no outliers. Now, why do we care about outliers? They will be important because an outlier can exert a lot of pull on your data, meaning it can cause your mean, your standard deviation, all of these things to be pulled kind of out of whack and make your descriptive statistics, seem confusing to interpret. And when we get farther along where you're actually using information to extrapolate and make future predictions, that can cause your predictions to be off to a specific degree. So what we tend to do is if we have an outlier, we eliminate that outlier, which is called Windsorizing our data. So we can go through again and calculate the z-scores for some other examples that we've done and see if we have any outliers there. So let's look back at our hotels example, and I can go through and I can insert here and calculate my z-scores. Okay, so down here, click in, standardize. Okay, open parentheses, select my x, my observation, comma, its mean. So first I ran descriptive statistics, then I just click on the mean. I'm going to F4 that because that mean is always going to be constant. I want to lock in that cell. The mean value will not change, even though the individual x will change, comma, my standard deviation. And again, I'm going to lock in that value as well. So I can drag this down. And here again, I have no outliers. No observations less than -3 or greater than less than -3 or greater than +3. So at this point, I would have you guys try that with this tax cost example, your data from question number 8. Box plots. Okay, box plots are picture summaries of data. There's 5 key points involved in here. You need the smallest value, the largest value, the first quartile, which is the 25th percentile, the median, and the third quartile or 75th percentile. You can get this information using Excel. So the min, the max, and the median will all come up when you do your descriptive statistics. You will, however, have to calculate the quartiles on your own. Box plot steps. This is kind of annoying because there is no real easy way to do this in Excel. I'll just describe the general process of what we're looking, how a box plot works. So you'll draw a box, literally just a square. Start with a blank piece of paper for your answer, draw a square. Locate its ends at the first and third quartile. So draw a timeline under that box and write in the number for the first quartile on the left-hand side of your box and write in the number of the third quartile on the right-hand side of your box. Then draw in a line for your median value. It can be, moved off to one side or the other. It doesn't necessarily have to be right in the middle. In fact, it usually isn't. Then calculate the interquartile range, which is Q3 minus Q1. Use that interquartile range to calculate an quote-unquote upper or lower limit. So the lower limit is 1.5 times the interquartile range. The lower limit, you start at Q1. You take Q1 and subtract from that 1.5 times the interquartile range. Calculate your upper limit, start at Q3, and add to that 1.5 times your interquartile range. Make notes of that on your timeline at the bottom, your number line at the bottom. Then you would draw dashed lines from the end of the box, which denotes your interquartile range, from the end of the box to the largest and smallest values within that upper and lower limit that we've discussed. So, 1, draw your box. 2, stick in a median value. 3, calculate interquartile range and the upper and lower limits associated with that range. 4, draw some dashed lines. Now notice that I'm saying specifically the largest and smallest values within that upper and lower limit based on the interquartile range. It's not necessarily the largest and smallest values overall. So you may, in fact, see an outlier there. That would be a value that is outside of the dashed lines you draw from the box. Okay, so let's see our example here. I gather all of my information. Smallest value, 425. Largest value, 615. First quartile, 445. Median, 475. Third quartile, 525. So I draw out my box. My box is located at the first and third quartiles. So the 425 and 525 denote, 425 and 525 denote my first and third quartiles. My median is in there at 475. Then I come up with my largest and smallest values based on my interquartile range. So my lowest, first I have to calculate my interquartile range, which is 80. So that is my 525 minus my 425. Okay. Then I take to get my lower limit, it's my first quartile minus 1.5 times my interquartile range is going to give me 325. My upper limit, my my third quartile times 1.5 plus my interquartile range is going to give me 645. So here I don't have any outliers because I don't have any observation. Here I don't have any outliers because I don't have any observations that fall outside of this dotted line region. Now notice it seems a little weird because I'm saying my lower limit is 325 and yet I don't even see that on the chart. The reason for that is because the absolute possible lowest rent was 425. So I'm going to stop my dashes there. Okay, then my upper limit goes to 645, but my largest observation that I had was 615. So everything is going to be falling within these whiskers, these dotted lines, and therefore there aren't any outliers in this example. Okay, so we've talked about variance. Variance applies when you're just looking at a single set of data and you want to know, how each observation relates to its mean. Covariance is when you're looking at the relationship between two sets of data. How do they relate to one another? So it's a measure of linear relationship between variables. Covariance can be either positive, meaning there's a positive relationship. When one goes up, the other goes up. Or negative, meaning it's an inverse relationship. When one goes up, the other goes down. So the Excel formula is covar, and then select your two sets of data side by side. Remember, you'd have to have two different columns of data. We're going to be focusing on this sample formula, and here again, you will be responsible for being able to calculate this relationship by hand. So remember, it's the sum of your first set of observations, the observation minus the mean, times that corresponding observation minus its mean, and all of that divided by n minus 1. Now, covariance can be used to help us determine the strength of a linear relationship. So our covariance really only tells us, do observations move with, do the data sets move with one another or against each other? The correlation coefficient tells us the degree of strength of those relationships. So a correlation coefficient can be between -1 and +1. Values near 1 indicate a strong relationship. So a value really close to -1 would be a very strong inverse relationship. A value very close to +1 would be a very close positive relationship. A value correlation coefficient value close to 0 would indicate a weak relationship between the two. So you use the covariance to determine whether the data sets move with each other or against each other, and then you use the correlation coefficient to determine how well they move with each other or against each other. So this formula here, this is saying correlation between x and y. The numerator is the covariance between x and y. The denominator is the standard deviation of x and the standard deviation of y. Okay, so here's an example. A golfer is interested in investigating what relationship, if any, exists between driving distance and an 18-hole score. So he calculates the sample covariance and comes up with a negative number. So that indicates that there's an inverse relationship between the distance and score. So as distance increases, score decreases. And then he calculates the sample correlation, and that number is close to -1. So that's going to indicate a strong inverse relationship there. And we can see the same calculations using the Excel functionality. So let's go and try some of this. Just looking at pure data, we're going to look at number 45. Okay. Click in here so I can tell you what page it's on. All right, this is number 45 on page 141. It just gives you 5 observations. It asks you to create a scatter plot. What indication does this, or what relationship does this indicate? And then compute variance, covariance, and correlation. So the first thing we're going to do is create a scatter plot. I highlight my data, insert, scatter, pick a picture. Wow, okay. So I see this relationship here. Let me see, something may be wrong. 3, 60. Okay, so yeah, this is fine. It's x first, then y. Always remember to do it that way. X is your horizontal, y is your vertical. So always set your data up x, then y. Now I can change that. I can change my chart layout to show me an actual equation, and I see my inverse relationship there. This does the best fit line that you remember from algebra, y equals mx plus b. So b is your vertical intercept, m is your slope, which in this case is negative. You can go through those calculations. You can also go back in design. We can play all around with the chart. It's really not all that exciting. Okay, so let's say I want to calculate let's insert a column in here so I can calculate mean. Okay, so get the mean of x, average x value is 8. I can drag that across and it will give me my average value of y. Then let's say I want my variance. Okay, my variance of x, highlight my x data. And I can do the same here, or I can just drag it across actually, instead of having to type in there, var. And my variance of y is 130. I can get my standard deviation. Okay. Equals STDEV. So standard deviation of my x observations, 5.43, and I can drag that across to do the same for my y. 11.4. So we see here, you're not really seeing any major change. Your values here are always bigger in your y region, and as a result of that, the variance and standard deviations are slightly larger. So now we are asked to calculate the covariance. Okay, the covariance of x and y. Just expand that column a little bit more. That is equal to covariance. Now highlight your data array for your first observation for x, comma, highlight your data for y. Close parenthesis, and that gives you your covariance. So this is saying that they inversely covary. And then I wanted to get the correlation coefficient. Okay, so I go over here, equals Quartile, array 1, highlight your data, your x data, array 2, highlight your y data. This tells me that there is, since this is relatively close to -1, it tells me that there is a strong negative relationship here. You can try number 46 where you do the same basic calculations and practice with that. Let's look now at question number 47. Let's bring this up. 10 major college football teams were played in January 2010, and the University of Alabama beating the University of Texas 37-21 to become the national champion in college football. The results of 10 bowl games are shown below. This is from 2010. The predicted winning point margin was based on Las Vegas betting odds approximately 1 week before the bowl game was played. For example, Auburn was predicted to beat Northwestern in the Outback Bowl by 5 points. The actual winning point margin for Auburn was 3 points. A negative winning point margin means that the team that won the bowl game was an underdog and expected to lose. For example, in the Rose Bowl, Ohio State was a 2-point underdog to Oregon and ended up winning by 9 points. Okay. So, first thing, develop a scatter diagram with the predicted point margin on the horizontal axis. Now remember, you always have to arrange your data x, comma, y. So horizontal axis, that's my x. So that means I do not need to change anything because predicted point margin is what the question is asking for on my horizontal axis. So I can highlight my data, insert a scatter plot, and I see my lovely scatter plot appear there. Question number 2, what is the relationship between predicted and actual points? Okay, so how would I go about calculating that relationship? What do I see here? Do I see a positive relationship or a negative relationship? I see a positive relationship. If I would like further confirmation of this, I can click on the layout where it actually where I can see the positive trend stuck in there, or I can click on one where it'll actually calculate, y equals mx plus b for me there, and I see my m, my slope coefficient, is in fact a positive number, so this is going to confirm that I am predicting a positive relationship in there. Compute and interpret the sample covariance. Okay. So my sample covariance, highlight my first data array, comma, my second data array, close parenthesis and enter, is 20.1. So that means that there is a positive relationship that I'm seeing there. And then it asks me to compute the sample correlation coefficient. Does this value indicate the relationship between Las Vegas predicted point margin and the actual, or what does this indicate about the relationship between the Las Vegas predicted point margin and the actual point margin? So I have a positive covariance, which would mean a positive relationship, And then I can calculate my correlation in the same way. And I come up with a positive number, but it's not really all that close to 1. So there is, you know, there is a relationship, but it's not an incredibly strong relationship between the predicted point margin and the actual point margin. And that is the end of our PowerPoint slides. Next, I suggest that you watch the video where we go over these calculations by hand, so you can practice that, and feel free to look at the additional practice problems and solutions that are posted for you on Blackboard.